this diagram shows you what it's actually based on. It kind of, stands on the shoulder of giants. And to implement the containers, it's leveraging a whole bit of technology that resides in the Linux kernel. So if you are asking a Docker to start a container at the top, Docker itself is leveraging either LXC or used to, and in a bigger way now libcontainer to interface with the Linux kernel. And inside of the Linux kernel, there's a few technologies that the whole thing relies on. It's the chroot that is basically a syscall that is responsible for changing what the root of the file system looks like from the processor's perspective. There are the namespaces, which control the isolation of what the process can see. For example, in terms of PIDs, we're going to take a look at that in a minute. But basically kind of categorizes what your process can see, and what is tricked into thinking is the reality. We have the C groups that limit the access to a specific set of resources. For example, we're going to take a look at how it's used to limit the RAM available to a container as well as CPU. We have the seccomp that is a mechanism for essentially limiting what syscalls, system calls a particular process can make. And with other things like SELinux and ARMOR, there's this entire security aspect that can be implemented. There are the capabilities that grant privileges that basically before capabilities, the super user could do everything and the user couldn't. And with capabilities, it's kind of broken down into smaller pieces that you can grant access to a particular user to do. And then there's networking, in which case there's a few different options that can be leveraged. And the file systems. And the file systems are interesting. We're also going to take a look at that in a minute, because Docker leverages UnionFS or similar file systems that allow for an efficient way of storing the data if you're using a lot of containers that share different things, share the same files rather. So this is like the high level overview of what bits are involved. And inside of the book, I'm going into detail about how to kind of poke, kick the tires of all these bits, and how to look under what's going on when you run a container and how these things are actually being used. In this session, I'm just going to try to show you enough to just kind of poke your interest and get you started. Hopefully, get you to buy the book. Let's now show you around a little bit the VM. So if you download and import the VM from GitHub, this is what it's going to look like. So inside of your home, there's going to be a folder called source. Inside of that source, I'm basically checking out all the source code that comes with the book, as well as the examples. And inside of the examples, you are going to see different chapters of different folders for different chapters, and in particular, the one that we'll be looking at today is the Popkin Docker one. You'll see that I've prepared 5 experiments. Hopefully, we'll have time to go through all 5 of them. I'm not sure if we're going to go on different tangents quite yet. I'm hoping to kind of see how this goes. But the plan is to show you like the basic chaos experiments that you might be wanting to do. I'm kind of making the assumption here that if you are watching this video, then you have some kind of interest in what chaos engineering is. But if you are new to that, let me just quickly switch the browser. This is what I basically consider the canonical definition of what chaos engineering is right now. If you go to www.principlesofchaos.org, this is the definition. So basically, the chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. Note that if you just googling that chaos engineering, one of the first things that you're going to see are breaking things on purpose or breaking things in production. But what chaos engineering really is just this experimentation on a system, and it can be a big system, it can be a complex system, or it can be as simple as a single process on the host. And by experimenting with it and seeing and confirming scientifically that your assumptions, what you think is going to happen, is actually happening when that situation is going on, that's where you create the value of chaos engineering. So what you typically do, kind of like the unit of chaos engineering, is a chaos experiment. And it is as simple as 4 steps. First, you look for a metric that can be reliably measured. Then you you measure the steady state. And if you are, let's say that, for example, we want to measure our application we think that our application is not going to be affected by some other event. Then we might pick a metric for observability that is, for example, a percentage of requests that are going through, successful requests. And that would be our observability metric that we can measure. And then the steady state would be that, yes, indeed, it's 100% okay. And then we introduce some kind of failure and we make a hypothesis, which is essentially a guesstimate of what we think is going to happen about the system. And then we run the experiment and we're either right or wrong. And we validate or we falsify our hypothesis. Let's go back to our VM. If you have used Docker before, you're going to be familiar with that, but I just wanted to kind of give you a quick overview first. So let's say that what happens when you run a container, these are the images that I currently have downloaded on my VM. This comes pre-configured. What happens when I do a Docker run, and let's say that I would like to use the option RM to delete the container when I'm done with it, TI for interactive access, and let's say that I want to run my Ubuntu focal. What happens when you start this container is that we have a brand new process, and all of the things that we saw applied before are working to kind of trick the process inside the container into thinking that it is an isolated machine, right? So for example, if I just look at my processes, you'll see that the bash that I'm running inside of this particular container thinks that I have a PID of 1. And the PS is PID of 8. Meanwhile, if I did the same thing from inside of my process here, I am already at PIDs in the 14,000s. Showing that, from just an observation like this, we see that there's already this isolation in terms of processes, the PIDs that we can see going on. If you're just starting with Docker and the chaos engineering, that's probably like one of the first things that you would like to check, right? Whether the PIDs or whether the things that are happening inside of the container can be affected by things running inside of other containers or potentially running on the host itself, right? So let's start with this as an idea for a first chaos experiment. Let's say that we wanted to check whether process, for example, that I'm running on my host here can be killed from inside the container. So in order to do that, the VM here comes with sort of experiment 2, a very simple script PID printer. As you can see, it's basically doing nothing. It's printing the date, then it's printing the PID, and then it's sleeping for 2 seconds. So this is done so that you can basically see easily the PID of the process, and you can see that it's still running because it's printing things every 2 seconds. Right? So if I wanted to now design a chaos experiment around that, probably one of the simplest chaos experiments that you can come up with, just to warm you up, it would be, okay, so my observability here is that I can see the process running, I can see its PID, and the steady state is that it is running, nothing bad is happening to it. And then my hypothesis would be, just an educated guess, that I know that containers are supposed to be isolated processes, so I shouldn't be able to just call this PID from inside of the container and kill it. And to implement that, we would do exactly that. We would take this PID, copy it, and go and try to kill it. So if I just open another tab now, and I start a container, let's say that I'm going to do that run. Again, I want to delete the container when I'm done with it. I want it to be interactive, and I want to run my Ubuntu 4.0. I'm now inside of my container. I can see it here that my bash has a PID of 1. Now, if I copy this 14380 process from here and from inside of the container, I'm going to try to kill it with just kill. I'm going to see, whoa, there is no such process, right? So that means that my hypothesis was right. That means that I was indeed in some kind of separated, isolated thing. And if we go back to the diagram of the technologies that were involved in Docker, this is what the namespaces are able to do for us. And just so that you are able to design meaningful chaos experiments, let's go and snoop around a little bit and see how namespaces are working. Back to the VM. I'm going to stop my little sleeper situation here. Just going to kill it. And actually, I'm going to kill this process too. And if you're new to the namespaces, man is your friend. You're going to see quite a lot of information here. This is man 7 of namespaces. But this is a good starting point. You don't really need to leave the terminal to get to know quite a lot about that. For example, the proc/PID namespace directory that we'll be looking into in a minute. But if you're completely new to namespaces, probably the first thing that you want to do is run ls, basically list namespaces. And if you run it as a user, this is what you're going to see. If you do run it with sudo, you're going to see slightly more of these things. But you can already kind of get an idea. You have the namespace number here. Then you have the type. And here you can see the different types. There's a month, there's a net, there's IPC, UTS, user, PID, and secret, right? And then you can see the number of processes in it, the first PID in that namespace, the user who runs it, and I think this is the first command corresponding to that PID. And if we just take a look at how many of these are there, we're starting with 18 namespaces by default. Now, if I go to the different tab, to the second tab, and we do the same thing again. We just start a random container that's not really doing anything apart from running a bash session. And we run this command here. we see that we have 5 new namespaces, right? So if I just drop the WC, you are going to see here where is our new stuff. This is the bin bash. So we see that our process 14,811 here has new namespaces. One for NAND, one for UTS, one for IPC, one for PID, one for NAT. And if I go ahead and kill this one, this process here, and count them again, boom, I'm back to the 18. So this already, if you know nothing about namespaces, is already showing you that the Docker is creating this new structure for them. Right? So let's take a look at this process here. Right? If you do PS of 14,987, you can see that this is our bash command, right? What else can we do? If we go back to our man namespaces, you can see, well, we have the description. A namespace wraps a global system resource in an abstraction, makes it appear to the process within a namespace that they have their own isolated instance of the global resource. And this is basically all that you need to know about namespaces in our context. There are the different types: the C group, the IPC, network, MAN, PIDs, or UTS, and all of them behave a little differently because they wrap different resources, but the idea is the same. It's to kind of trick your process into thinking that the resource that it's using is for them only. The thing that I mentioned before, this is kind of interesting, you probably should know that, is that you can get a lot of information about the namespaces that you get for the process just by using the sudo file system in /proc/namespace. This is giving you an example of, for example, checking the namespaces of the current process, and you can see that. Instead of doing that, let's see the namespaces of our container process. So we found here kind of manually looked for this particular PID. If we just copy that and then we do ln ls of proc/our PID namespaces with sudo, we're going to get a list of these links. Right, and notice that these are symbolic links, and they are kind of funny because if you try to just kind of follow them, for example, if I try to do secret here, if I try to ever go there, interesting. If I try to, for example, read link on that. This follows this interesting format that this is the type of the namespace, and then within this brackets you get the actual namespace of it, the namespace number of it. This is just giving you like kind of a vague idea that Docker is doing something and telling the kernel to create some kind of isolated namespace that is tricking the process into thinking that it has a completely different PID tree to what it actually is happening on the host itself. Yeah. So if we wanted to dig a little bit deeper into that, within the book, I'm going to more details and trying to kind of explain how all of this fits together, and giving you resources to learn more about what's going on in there. There's also, if you're interested, I am providing you with a kind of, if you go and take a look at Containerish 2, I'm showing you how to use unshare to run a process within a particular namespace without using Docker. So if you remember, maybe you noticed that in the man namespaces, it's also mentioning here the API to use the namespaces. And the particular three things that are of interest are the clone, the set namespace, setNS, and unshare. And unshare allows you to basically start a new process within a particular namespace. And if we have time, we're going to go back to that, and we're going to try to see how we could achieve a result that is similar to what Docker is setting out using these two scripts here.